PhD from University of Chile in Santiago, and also her postdoc. First postdoc was at PUC, and the second postdoc was at ISO. She was an ISO fellow at Garching, and since then she has become a staff member for about a year and a half, and now she's visiting our group and the IAG for a few days. In fact, she's leaving today, so she may still have some time this afternoon to talk if you like to discuss her science topic. Thanks a lot, Paula. We're really happy to have you here.
Thanks for the invitation. Okay, I hope it's not too dark. Can you see me? Okay, so thanks for the invitation. So today we'd like to tell you how we can use machine learning to search for diverse AGN populations. Yes, so just a reminder in case you don't know what are AGNs. So these are systems in the nucleus of the galaxies where you have a supermassive black hole with masses larger than 10 to the 6 solar masses that are actively accreting material, and these release a lot of light and energy. And one of the key properties of AGNs is that they are variable. So the variability seems to be described by a stochastic process, and here you can see an example of a typical AGN Lie curve. And the characteristic time scale can range from a few hours to several years. And these characteristic time scales can be seen here, where we have the Fourier transformation of the Lie curve. And you can see here that okay. Should I start from the beginning or? Okay, well, yeah, it's okay. I can start from the beginning. Okay, so you already hear this, but just for the people online. So today we'll tell you about how we can use machine learning to search for diverse AGN populations. So as you know, AGNs are these sources located in the nucleus of some galaxies where we have supermassive black holes with masses larger than 10 to the 6 solar masses. And these systems are actively accreting material, so that's why they're active. And in this accretion process, there is a very high release of energy and light. And that's why we can see them. So one of the key characteristics of AGNs is that they're variable, and the variability seems to be stochastic. And they have time scales from the variations that range from a few hours to several years. And this time scale can be seen here. So this is the typical AGN Lie curve, and here is the Fourier transformation of an AGN Lie curve, and you can see this more or less bend power law. So where is this bend is the characteristic time scale of the variation. So this bend can happen depending on the black hole mass at different time scales. So if you see these properties and compare them with the typical physical properties of AGNs, like the black hole mass, the luminosity, the Eddington rate, you can see that there is a correlation between these variability properties and the physical properties. So here you can see the effect of changing, for instance, the Eddington rate, where you will have higher amplitudes in lower Eddington rate systems, and the black hole mass changed the time scale. So systems with larger masses will have longer time scales. So this is why variability is very efficient to detect systems with different masses and Eddington rate, but in particular, low mass and low Eddington rate. So normally if you search for AGNs with typical methods like color cuts, you will be very sensitive to the more luminous and the more massive objects, but with variability, you can select this low end in the distribution. And also something that has been proposed since several years is this unification model, where in the optical range, we say that if the source shows broad lines, it's a type 1 AGN. If there are no broad lines, only narrow lines, it's a type 2 AGN. And normally people explain this by the viewing angle. So if you have access to the innermost part, you have broad lines because you see the broad line region. But if you have the dusty torus in between, you don't have access to the innermost part. But this scheme was challenged by changing state AGNs, because they show transitions between these two classes, type 1 or type 2, in very short time scales. And you cannot explain this change in the classification just due to viewing angle effects. You will need to rotate the whole system, which has the size of like more or less the solar system, to explain this. And that's unphysical, right? So now we are aiming at studying this changing look agents or changing state agents to understand what is the physical mechanism behind these transitions. But we know that most of them are detected also in light curves like this. They show a big drop in the flux or a big increment in the flux, depending on if it's a turn on or a turn off source. So in this example is the first changing look agent that was detected in the optical, where you see here that at first it had plot lines, and then a few years later it didn't have plot lines. So we cannot explain this from the unification model. So that's the motivation of this changes survey. I don't know if you know about Foremost. So this is an instrument that will be installed in the next weeks in VISTA. So VISTA is a telescope that is in Paranal. Here you can see the telescope. And they just approved the delivery of some parts to Chile. So now in more or less October, we will start the commissioning. So the survey will start more or less in the first quarter of the next year. And this survey is a survey facility. And Changes is one of the AGN surveys that was approved for Foremost. So all the surveys share the same focal plane. And in total, there are around 2.4K fibers and also some low resolution fibers. So it's a big challenge to coordinate all these surveys, but it will release a huge amount of data, in particular in the optical range. So Changes is interested in studying AGNs in the southern hemisphere. And in particular, we want to understand these transitions between sources with very low accretion states and very high accretion states, like changing look AGNs, but also normal AGNs at different levels of accretion. So we have three main key motivations. One is to characterize the low end in black hole mass and Eddington rate, but also investigate correlations between the properties of AGNs and the variability properties. And finally, to find very rare subsamples like changing look AGNs, tidal disruption events, or extreme variability. So today we'll tell you the tools that we're using to select sources for Changes. So Changes is starting next year, but we already needed to define the catalogs for the survey last year. I think the deadline was mid-2024. So it's important to select them from already available surveys. So at the moment, we have been using CTF data, particularly for the variability selection. But we also have other selections, but I don't have the time to explain it today. So I will focus on these two selection techniques. One is a variability selection, and then an anomaly detection. So let's go first with the variability selection. So as I said before, AGNs are variable, and this tool is very helpful to find them, in particular at lower masses and lower Eddington rates. And we're using data from the Zwicky Transient Facility. So this is a telescope that is in the northern hemisphere, it's in Palomar, and is a small telescope, but with a huge field of view. So you can see here, compared to other cameras, it has 47 square degrees. So it's very efficient in scanning the sky. We have more or less every 2 nights a new image for the same field. And the public data includes the G and the R bands, and the I band is private. So there are 3 main data products from CTF. One is alert stream. Maybe you already know about brokers. So this is the data that is processed by alert brokers. And in this case, what we use is this PSF photometry measure on the difference images. And whenever there is a 5 sigma detection in these images, there is an alert released by CTF. So this difference is basically you have a template that was constructed at the beginning of the survey, and then you subtract the template, the science image, which is the image of the night. You subtract it, the template. But this only gives you the most variable observations, the most variable objects, or the transients. If you want to have access to the whole data, you can use the data releases. And this is PSF photometry over all the science images. So not the difference, but the science. The problem of this is that it's PSF photometry, so it's not suitable for extended objects. And that can produce problems. So, but I will tell you later how we can solve this problem. And then you have the force photometry. So this tool, unfortunately, is not very user-friendly. We only have access to 1,500 LSST per day, and you get the data in an email. So it's not very efficient, especially if you want to classify the whole sky. But the force photometry is the best data because it's the force photometry over the difference images for all the images, not only the alerts. So this is the cleanest data and the one that contains the more complete LSST. So we are using these 3 data sets to find AGNs. So first, let me tell you about the alerts. So this is a collaboration that has been going on since 2018. The ALeRCE broker, which is one of the official brokers for LSST, is based in Chile. So it's the only broker that has the main, like the headquarters in South America. We also have FINC in France that has a lot of people involved in Brazil. And the rest are mostly based in the Northern Hemisphere. So ALeRCE is now processing the CTF alert stream to be ready once Rubin starts operating this year. So this year we finally can say LSST will start operating. But CTF is 10 times smaller than LSST in terms of the amount of data that it produces. So we need to take this into account when we prepare the models. And we have 2 flavors of models available. One is the stamp classifier that for each new alert for a new object, it classifies the sources into 5 classes using only the images. And then when we have more complete light curves, we use the light curve classifier that is able to classify in a more extended taxonomy. So let's go first to the stamp classifier. This is not particularly useful for AGNs, but if you're interested in transients, it's super nice to detect early transients. So for instance, a supernova as soon as it explodes. In this case, we use a convolutional neural network that where the input is the 3 images from the alert, and we rotate them in different angles. And then with convolutional layers, we extract the patterns. Then we combine these patterns in a dense layer, and then this is what we use for a dense neural network to classify. As you can see here, the confusion metric. So it works quite well, but for AGNs, it's not ideal because it will only give you sources that are maybe not only AGNs, but also maybe data disruption events or anything that is nuclear. So for AGNs, we use instead the light curves. So this is the light curve classifier. It's based on the light curves that we can construct from the detections. That is all the 5 sigma detections in the difference images, as you can see here. But we also use the non-detections. That means all the difference images where we don't have a 5 sigma detection. And CTF for this provides upper limits. So as we use light curves and we have 2 bands, we can have a much broader taxonomy. So in this case, we first separate the sources as transient, stochastic, and periodic. And then in another level, we separate with a broader taxonomy. So for the case of AGNs, we have these 3 classes: blazar or jet-dominated, quasar or core-dominated, and AGN or host-dominated. So to do this, we have several features. We have 152 in total, and we fit this to a random forest algorithm that is a hierarchical balanced random forest. And there are several features that we use here, but particularly for AGNs, the most important ones are these 2, the irregular autoregressive model and the Mexican hat power spectrum. And we define these features in a way that now we are using them with CTF, but in the next months, we will use them for Rubin data. And we also include metadata from other surveys because we noted that only the light curves cannot give you very pure samples. So we also include data from Allwise and Gaia, as well as Panzers. So these are the main features that are relevant for AGNs. The Mexican hat power spectrum is basically a way to isolate the variance of a time series in a given window of time. So you define this Mexican hat filter with a time scale that is the time scale that you want to isolate. And particularly for classification, we noted that if we use 10 days and 100 days, we can very well separate AGNs from other classes. And you can see here the effect of applying this Mexican hat filter to the same light curve. So this is an X-ray light curve with very high cadence, and then you see here the effect of applying the filter at different time scales. So with this, you can measure this low resolution power spectral density, where you can see the power law of AGNs. But also another parameter that was super useful was this irregular autoregressive model that is basically a way to measure the level of autocorrelation in a Lie curve, but when you have a regular sampling. Because most of the autocorrelation methods available in the literature are using even sampling, and in this case, of course, in astronomy, that's impossible. So this parameter here gives you the level of autocorrelation when the Lie curve is sparse and it has gaps. And we can see here that it works very well separating quasars from other classes of variable objects. And also something that is very relevant for AGNs is this damp random walk model, because we know that AGNs are stochastic, and we can use a very simple stochastic model like a damp random walk to characterize the Lie curves, where this tau here is the time scale where we have this bend in the Fourier transformation, and sigma is the amplitude of the Lie curve. And we can use this to separate very well different classes of AGNs. So blazars tend to be here, AGNs in the middle, and quasars here. So we are using all these features to classify. And that's why we have very good results. Even though we are using a random forest at the moment, none of the models available in ALeRCE using deep learning are able to give better results than this random forest. And it's because we use very different statistics, very diverse statistics that are able to characterize different classes of objects. So here are the results. I'm highlighting here the AGN classes. So most of the confusion is only between the AGN classes. We don't see much confusion with other classes. And here you can see the fraction of candidates. This was obtained in 2021. But the problem with ALeRCE is that the densities you obtain are very low. So you can see here a density map of all the AGN candidates, including the 3 classes. And you can see that at most we have 5 or 10 AGNs per square degree. And that's very low, because for changes we need more, because we have access to 1.5 fibers hours, so we need more targets. So that's why we decided to not only use ALeRCE, but to move on and use the data releases. But the problem with the data releases is that this is PSF photometry over science images, and there is no correction by sync variations. So if you see the Lie curve of a non-variable galaxy in the data releases, you will see a variable source. And this is just variations in the weather conditions and the sync, because the amount of light from the galaxy that enters the PSF can vary. If you use the data releases for point sources, like non-variable stars, you will see a flat Lie curve. So this is what you will expect. But for extended objects, that's not the case. So this is an AGN. You still can detect the variability, but you see some variations that are just due to these spurious variations. And you can still detect transients, but this is highly hidden in this noise. So we somehow managed to use this data to classify sources. So for this model, we decided to use only 1 band per model, not combined in multiple bands, because it's tricky to combine bands with the data releases. So we only have single band features, but also we included colors from different surveys to have information about the color of the sources. So in this case, we also have a hierarchical taxonomy 3, but we added this level where we separate first the sources as variable, and these also include transients, and non-variable galaxy or non-variable extended object, and non-variable star. And in the case of the AGNs, now we decided to separate them in terms of redshift, because for changes we needed to have an idea of the redshift of the source, so we can provide an idea of the redshift for the estimation of the exposure times. So in this case, this works because we have the proper features. So you can see here the features that I was mentioning before. When we compare non-variable stars, non-variable AGNs, non-variable galaxies, and AGNs. So if you use the features that people normally use in AGN science, like the excess variance, is typically used. It's basically the intrinsic standard deviation of the Lie curve. You will see that AGNs and galaxies show the same values. This is a big problem. We cannot separate AGNs and galaxies using this parameter. But if we use the other features that we included in the model, like this irregular autocorrelation function, or the time scale of the damp random walk, or the Mexican hat features, now we can separate these samples. So that's why we are able to separate AGNs from galaxies, although we have this huge amount of noise in the data release layers. So that's why here you can see in the results, we can separate AGNs from non-variable galaxies. So here are the non-variable galaxies, and we miss some of the low redshift AGNs, and we classify them as non-variable galaxies. And this is because they are host dominated, and they are very affected by the spurious variations due to the seeing variations. But we still miss only 36% of them. But maybe here we have the most important objects. So that's why we decided to move one step further and also use the force photometry that I will tell you later. But finally now we have good numbers for AGNs. So if you see this density map now, we have a peak at 32 AGNs per square degree. So this is much better for what we wanted to have for changes. But still, as I mentioned before, we are missing a big fraction of low redshift galaxies. And we are interested in particular in the low redshift sample because it's probably there where we will see the low mass and low Eddington rate population. So that's why we decided to move on to the force photometry. Why? Because as I mentioned at the beginning, ALeRCEs are incomplete. They're very nice, but they won't give you the same number of epochs for the same object. So this is the same object seen in the ALeRCEs and seen in the data release. The data release is totally noisy, so it's very hard to obtain proper classifications. If you see the force photometry data, then you see a very complete light curve and much cleaner in terms of signal to noise.
Can I ask a question?
Yeah, sure.
I will ask the question. So my take on this first part of the presentation is that simple classical methods like random forest, they work pretty well, and you guys spend a lot of time with feature engineering.
Yes, that's the key part.
And lots of groups find the same result, that classical methods, they work super
very
fine.
well. Yeah.
You don't need to do deep learning, transformers,
yep.
sort of stuff.
Exactly.
So my question is, where does time get? Is time relevant here?
Timing.
Is time domain relevant here?
Oh, yes.
What temporal feature are you using? Like the break in the power spectrum?
Yes, that's the tau of the damp random walk.
Okay. And that's the only temporal information you use. The break?
No. So okay. So we have, as I mentioned before, 152 features. I didn't have the time to explain all of them, but okay, the damp random walk gives you an idea of the time. We also have periodograms. We have the regular autocorrelation that is an autocorrelation, but it's a measure of the time because it's autocorrelation as a function of time. So then you have the characteristic time scale of the light. And we also have other features like for supernovae, we have the supernova parametric model where we can see the time scale of the transient. So yeah, there are several features, but I'm highlighting here the ones that are more relevant for AGNs. Okay, let's go back. Okay, so the force photometry data is the more complete, the cleanest, but as I mentioned at the beginning, we only can get from CTF 1,500 light curves per day. And you need to specify which targets you are looking for. So if you want to classify hopefully millions or billions of objects, you cannot use the CTF services. So what we did was to do our own force photometry. So we went to the data releases where you can also get the images. And we ran by ourselves the force photometry. And we do this only in the area that overlaps CTF and FORMOS because it was super expensive to do this. And we use aperture photometry instead of PSF because this is more adequate for extended objects. So this is what we use. And you can see here the differences in the features when you have non-variable objects and AGNs. So for instance, here is this p-bar, which is the probability of having a variable light curve. And if you don't use force photometry, but instead you use the data release light curves, you will see that a high fraction of the sources, like galaxies, are classified as variable. But if you go to the force photometry here in blue, the galaxies are now non-variable, as expected. So here we remove this problem of the PSF affecting the flux. And the same for the non-variable stars and the different classes of AGNs. So with this model, we hope to find the population that is missing in the data release. So we use the same hierarchical taxonomy and the same attributes as before for the data list, and we were able to identify now similar numbers of targets per square degree. And now we only miss 13% of the sources as the low redshift ones as non-variable galaxies. So we were able to recover almost 20% of them. So we are still missing sources, but this is because CTF is very shallow. The limiting magnitude is 20.5, sorry. So is what we can do with the data. But this is the best you can do with the data for AGNs in terms of classification. So that's the first part. So with this sample, we created a catalog of AGNs for changes that is already like defined. We cannot modify it. But we also have LSST that will come this June. I think it's the first release of the commissioning camera images. So we also have some time dedicated to target of opportunity observations to follow up sources detected by LSST, because we cannot include a catalog of LSST now, and Foremost doesn't allow us to modify the catalogs. We decided to have this additional survey only using TOO time, and it's particularly to target transients or changing look AGNs. So we needed to have a model now for the TOs. So this is the second part of the talk, how to identify changing look AGNs using anomaly detection. And just to highlight, this is the work that will be complemented with Raquel, who is here. So she will visit me at ESO, and we will update all the things that I'm mentioning now. She will improve the models. So how can we do anomaly detection with light curves? You have two options. You can do out of distribution anomaly detection and search for objects that are very rare respect to a general sample. But you also have contextual anomaly, when for a given moment you have a source that was normal and suddenly is doing something unusual, but then it can be back to normal. And you can identify these anomalies by using contextual anomaly detection. So let's see first the out of distribution anomaly detection, which is the more classical anomaly detection. And a very popular model that people use for this is isolation forest, which is similar to a random forest or a decision tree. But in this case, what we do is to isolate all the objects in a sample, and we measure the number of splits that we need in the tree to isolate each object. The ones that are more anomalous will require very few splits. Like this one, it's only one split to be separated from the rest. And the more normal ones require more splits. So you can use this as a metric to identify anomalous objects. But then how we can do anomaly detection with contextual anomaly. For this, you can use deep learning. In particular, a very useful tool is variational autoencoders. So this is a modification of the more traditional autoencoder, where you compress the data into a latent space, and then you use that to generate a new version of the image, like a reconstruction, or it can be an image or a light curve, etc. In a variational autoencoder, the main difference is that we have this encoder that compresses information, but then we have a latent space that is the one that contains the main properties of the data in a compressed version. But this is a probabilistic distribution. So we have, for each element in this latent space, we have a mean and a variance. And thanks to that, we can generate different versions of this latent space and generate different versions of the data. So for instance, here we can take a random distribution of following this probability distribution, and then generate new properties, and then have different versions of the data that are very similar, but they're not the same. So this is particularly useful for anomaly detection because it allows you to have sources that are similar, very close in the latent space. If you don't do this, you can have very similar objects that are very separated in the latent space. So how would you do anomaly detection here? First, then you compress the data with encoder. Then you have a set of attributes that is the latent space. And you can use this instead of having your own statistics, like the average, the standard deviation, the amplitude, blah, blah, blah. Instead of that, you provide this latent space as a set of attributes to an isolation forest model. But then you can also use the error of the reconstruction as an anomaly score, because sources that are normal will be easy to reconstruct with this model, and anomalous objects, the model will not be able to reconstruct them properly. So you can use these two ways to do anomaly detection. And why we are using this for changing look AGNs or changing state AGNs? So I don't know if you remember from the beginning of my talk that changing look AGNs are these sources that change their classification as type 1 or type 2. And we also see a very anomalous behavior in the light curves. And this was confirmed in this paper by Suberlac 2021, where they noted that all the changing state AGNs in their sample were anomalous compared to the normal population of AGNs. So after this paper, we got inspired and we decided to try anomaly detection and see if we can identify sources with this approach. So for this, we use a variational recurrent autoencoder. So it's a version of variational autoencoders where the encoder and the decoder are recurrent neural networks, because we're using time series, so it's better to use recurrent neural networks. And the parent sample that we used was all the AGNs, known AGNs from these two catalogs, Milliquas and Roma catalogs, with light curves in CTF. At the moment of this work, we were using datasets 5. Raquel now will use datasets 24, I think. So it's been a long time since we ran this the first time. And we trained this, so this model is unsupervised. But in order to avoid finding that the most luminous or the less luminous objects are the most anomalous, we trained the model using a balanced training set. So you can see here that we use the physical properties of the sources for which we have access to SDSS data to define a training set that was balanced in terms of luminosity and black hole mass. So from this, we avoid problems in the identification of anomalies. And we also balance the data in terms of the properties of the light curves themselves. So we use a balanced number of detections in each light curve. So then we train the model with this balanced training set, and then we apply the model to all the data. And we first use contextual anomaly detection to identify the sources for which we couldn't reconstruct properly the data. So here in black, you have the input, and in red, the reconstruction. So you can see here that this is not reconstructed properly. So we use this reconstruction error, that is defined here, as an anomaly score. And we selected all the sources with a reconstruction error larger than 3 as anomalies. And we use here as a control sample the blazars, because blazars tend to be very rare compared to AGNs in terms of variability. So we decided to use this cut here because that includes most of the blazars without including most of the quasars.
What physical properties do you use to balance the data set?
The luminosity and the black hole mass. Okay, I think no, too far. How do I? This. Sorry. Also. Okay, so we also then use, for the ones with good reconstruction errors, we use as an additional step the latent space as a set of attributes. And we use, here you can see the distribution of these attributes. And we use isolation forest with this input. So instead of using the features that we were using before for classification, we only use the latent space. And you can see here that we selected the 2% more anomalous objects as candidates. So following this approach, we were able to identify almost 9,000 objects. Here you see the control sample of blazars. A high fraction of them is classified as anomalous. And then we inspected the sources that we classified as anomalous. Unfortunately, we noted that a good fraction of them, almost 90% of them, were problems in the images. And these images were hard to remove following the recipe that CTF proposed to remove bad epochs from the data releases, because there was no way to see in the light curves that this was a ghost, for example, or a reflection of the instrument. So this method can also be used to clean data sets. It's a second use case. And also we noted that a good fraction of them were sources that were misclassified as quasars in the original catalog. Some of them were cataclysmic variables and some were YSOs. So that's why they were classified as anomalies, because there were no AGNs. But after removing the bad epochs and the candidates that were not AGNs, we selected all the sources that were showing a drastic flare or a drastic increment or decrement in the luminosity as candidates. And we identified 75 of them. So you can see here some examples of candidates. We had data now to confirm the nature of the sources, so we are working on this. But we already know from the literature that at least 6 of them are confirmed, and half of them were candidates in other works, like this work by Matthew Graham that is in preparation. Okay, so that's the methods. Now let me tell you some science. So because we are using this now, although Foremost hasn't started yet, we are already using this for science. So what had we discovered with CTF at the moment? We did a pilot project to see if we are able to identify changing look AGNs. So for this case, what we used was to select all the type 2 AGNs known in the literature that were classified as type 1 AGNs by our model, by our LSST classifiers. And we were able to confirm 19 new changing state AGNs following this approach. So this was presented in 2 papers led by my student Elena Lopez Navas. Then, in a more recent work, another student, Santiago Bernal, used the classification that we have for the 3 models, the ALeRCE, force photometry, and data release, to see which of them are located in low mass galaxies, because we wanted to find low mass AGNs. And from this, we were able to identify 500 sources that were in low mass galaxies with masses lower than 10 to the 10 solar masses. And of them, 400 of them more or less had a good quality SDSS spectra, and we were able to confirm 87% of them as AGNs, because they had very tiny broad lines or they were AGNs in the BPT diagram. And something very interesting about this work is that we found for the sources in the eROSITA sky that 67% of them had a counterpart in eROSITA data release 1. I don't know if you heard about a work that was exploring all the sources that were classified as AGN in low mass galaxies with variability before our work, and they were able only to find 1% of counterparts in eROSITA. We are finding 67%. So probably these other works had very high levels of contamination from other classes. And then this is something that is very interesting for me, is the identification of newborn AGNs. These are sources that were several years ago start forming galaxies, but now you see that they are type 1 AGNs. So this source was identified by checking all the known sources in SDSS that were classified as star-forming galaxies and that were classified as AGN by our models. And for one of them, we could see clearly the appearance of broad lines. But more recently, I led this work where we presented the probable awakening of a 10 to the 6 solar mass black hole. So this source, well, this is the light curve that is in the paper, but the light curve continues, so it's not yet faded. And it started showing alerts in CTF at the end of 2019. If you only see the alerts, you will classify this as an AGN, and that's why we identified this source. I was looking for AGNs in dwarf galaxies, and I found this source. But then when the data release became available, I noted that the source was not variable before. So then I went to other data releases from other surveys like Catalina, Assassin, Gaia, and WISE, and the source was not variable for 20 years. Only now is showing activity. So then we started a follow-up campaign. We observed the source with different facilities, and we could see the evolution of the source in the BPT diagram. So in early data, before the event, the source was classified as a star-forming or composite, depending on the survey. Then after the event, the source moved here in this, like the corner of where you have AGNs or galaxies, and then now the source is here. If you see the source now, it's a type 2 AGN. We don't yet see broad lines, but we saw the variability of the oxygen 3 line, which is very rare, and now the source is a type 2 AGN. And recently also we noted that the source started emitting in X-rays. The source was not emitting in X-rays for multiple years. We explored all the archival data, Rosita, Swift, everything available. And we also followed up the source with Swift for several years. Only until February 2024, we had the first detection. And with Chandra, we were able to confirm that this detection was nuclear. And recently, we published this paper in Nature Astronomy, where we showed that the source is now showing QPs, quasi-periodic eruptions. So the X-ray emission that we were seeing is from these quasi-periodic eruptions. And these are X-ray flares, very soft. And normally, they were expected to last up to maximum 1 day, the recurrence time between the different flares. But this source has a separation of 4.5 days. Normally, these sources are explained by these extreme mass raging spirals, where you have a black hole with an accretion disk, and then you have a star that is orbiting the system. And whenever the star crosses the accretion disk, you have a shock wave that produces these flares in the soft X-rays. But this is the first case where the time scale is very large and is not associated to a tidal disruption event, because normally these sources were associated to tidal disruption events. And also we could see that it's variable in the UV, and this has been not seen before. So this is the first paper that shows the QPs. Now we have another paper that was submitted where we see that, I don't have a slide, but we see that now this time scale is even larger. Now it's 10 days instead of 4 days. So yeah, we hope that paper will come soon. I cannot show the plots because it's under review, but this is even more extreme than we showed in this paper recently. And finally, we also were able to identify a tidal disruption event, but of a cloud in a binary supermassive black hole. And this was identified using the STAMP classifier that I presented at the beginning. This source was first classified as a supernovae by the STAMP classifier, but then we noted that the source was already classified as AGN by optical spectroscopy. And then we noted that the source started showing this periodic evolution. That is quasi-periodic because the amplitudes are very different. And from models by Djokovic 2026, we were able to reproduce this with a tidal disruption of a cloud in a binary supermassive black hole. So yes, that's it. We had been using CTF to classify sources for changes, but we didn't stop there. We are now using currently these models to identify very rare objects. So my take-home message here is that in order to have complete and diverse AGN populations, you need to combine different classification techniques. Not only the ALeRCE will give you the answer, not only the data list, not only the first photometry. You need to combine them to find the very interesting objects. And that's it. Thank you.
Thank you, Paula. Very nice talk. We have time for questions.
Thanks for the talk. Very interesting. Let me, you know, from the classification, you identified a subsample of, let's say, 60, because you mentioned the 60% of objects that were anomalous in your sample, and then a percentage of those you could identify with non-catalogs quasars, right? QSOs. Yeah, but only I think 65% out of 75%.
So this is okay. Let me go back. I think you're referring to this, right? This 65% here.
Yeah.
Yeah, this is just because okay, I didn't give much detail about this, but in the parent catalog we have quasars, AGNs, blazars, and also then radio galaxies. So among all the sources that we identified as anomalous, 65% were regular AGNs in the previous catalogs. Now we need to see in the new data if they are maybe type 2 AGNs now, because several of them were like this, like sources that were bright and then they fade. So probably the data was not for all the cases, but for some cases we have SDSS data at the beginning of CTF, and now we need to see what the sources are doing now, because probably they now are turn off AGNs, so they are type 2s.
Right, but still, because you try to identify those sources with anomalies, right? But anomalies means some kind of variability.
Yes.
Right? So out of a population that in general lines should be less variable population,
yes.
right?
Yes, so actually that's the advantage of using anomaly detection, because most of the, I don't have a slide for this, but previous work selecting changing state agents were selecting only the extreme variables. So more than one amplitude variability in 1 year. In this case, we only selected the ones that were anomalous, regardless of their amplitude. So they could be not super variable. Actually, this source, this one, if you see this in magnitudes, the amplitude is 0.3 magnitudes. Right. So very, very faint compared to other sources.
Right. And of course, you did use this methodology for a given band, right?
Yes.
Constrained band.
Yes.
But it could be also applied to any.
Yes.
Right?
So that's the work that Raquel will do with me at ISO to update the model so it's able to deal with multiple bands.
Right. Okay. Thank you.
Hello, thank you so much for your talk. I have a few questions, if I may, but the first one is you mentioned the excess variance parameter,
Yes.
and then you also said that you use several other parameters, and that the excess variance is good for variability, but not really to classify between galaxies. And then you also mentioned that you use the autocorrelation. I was wondering, could you talk a little more about other parameters that you may use when including variability, and also how do you deal with the gaps in the light curves?
Okay. So first, related to the excess variance, if you don't have the problem of the data releases where you have spurious variations, you can use excess variance. So if your light curves are well defined and the photometry is good, it's a good metric. The problem is when you have noisy data, and this is the case for the data releases. So you cannot use excess variance. And I unfortunately have seen papers that use the excess variance with data releases, and they conclude that every galaxy in the universe is variable. Of course, because you have spurious variations. But then, for instance, the gaps are very well characterized by this regular autocorrelation function, because we include the, okay, let me go back to here. We model this. It's part of the model, the separation between epochs. And we use a Kalman filter to measure this properly. I can send you the paper if you want more details.
Yes, please.
And then, also the Mexican hat is very good with gaps, because basically what you do is to convolve the light curve. Here you have huge gaps with this Mexican hat filter to isolate the variance at a given time scale, and then you measure the variance there, regardless of the separation between points. And then, well, in the paper, you can see in this paper from 21, the 152 features. There are a lot. We have a clear description of the features there.
Okay, I would really appreciate if you can send paper. Thank you. And just a last question. You also commented that you used time beings of 10 days and then 100 days. Why specifically those cadences instead of 1 month or 6 months, for example?
Okay, I don't have the plot here. It's in the paper, but it was basically inspired because we had a lot of contamination from long period variables in the AGN class. And long period variables are periodic or semi-periodic variable stars, where at long time scales you see variability, but at short time scale you don't see variability. So 10 days were not sensitive for long period variables, 100 days were sensitive. So in that case, we were able to separate these two populations.
Hi, Paula. Can you go back to your huge confusion matrix there with the AGNs together with everything else? So my question is with the respect to LSST. So it's going to be deeper. Maybe you can have smaller apertures, but also the luminosity functions mean that you're gonna have different numbers. So what is the let's say the standard thinking from the experts? Is it going to get better or worse with LSST?
Definitely better for instance, for the alerts. We will now be sensitive to variability at low amplitude, so this problem with the density will be solved at some magnitude. That I asked the people in Rubin if they had like characterized properly the magnitude error at a given magnitude, and they say yes, but this will be properly characterized during commissioning. So, but they say at least up to. So the problem with CTF with this 5 sigma happens around 18 magnitudes. In LSST will be at 22nd magnitude. So at least we will have 5 more magnitudes deeper to be able to detect sources in the alerts. But the problem here is that our training sets are very bright. All the AGNs we know, from DESI now we have much deeper samples for AGNs, but particularly for transients, we have very bright known objects. So what we are doing now is to use simulated data. So we are training the models with Elastic, which is the simulated challenge, and the models will be fine-tuned then later to properly classify the LSST data. But that's a big problem.
The LSST is going to provide force photometry with the proximity.
Yeah, so LSST in the alerts, the day after, not exactly with the alert package, you will see force photometry I think 1 year before. But this will be included a few hours later because it's in terms of bandwidth, it's very expensive. So brokers will have access to these packages a day after, and then we will include them so users can see them without any issues.
Yeah, I have a question about your changing look AGNs. So in my opinion, this is one of the most interesting open problems in the AGN community, the nature of changing look AGNs. And we have no idea what's happening there, right? So we have no idea what's driving we have some ideas of what's driving what makes such a dramatic change in the AGN state. So I was wondering, since we don't even have an understanding of what's happening there, how homogeneous is your sample of changing look AGNs? You know, I'm wondering whether you could have in your sample things that are changing for dramatically different reasons. You know, like it could be, you know what I mean. Yes. So that's my question.
Yes, yeah. That's a very good question. So unfortunately, all the selections that we have available now were targeting extreme variability. I think this work is the first one that targets any kind of anomalous variations. But still, we need to confirm in real time these sources because this was done with archival data. So now what we need is a model that works in real time so we can follow up the sources right after they transition. There is only one case where we did this, but it was also a very extreme event. So in my opinion, the best way to identify a very general sample is by comparing optical spectra from several years ago and now. But
you're not doing that, right?
No, but it's my plan for the next years. My plan is to take all the available optical spectra, publicly available, and compare this with the Formos data. Because with Formos, we will have every night new observations. So if we see a transition in Formos, we can follow up the target later with more facilities. But yeah, it's a big problem. We know that it's the tip of the iceberg. We need to now go to the whole iceberg.
Here.
Oh. Where? I don't see.
There.
Two quick questions. Your 75 candidates that you found, what is the redshift distribution of those and the X-ray properties?
So of which candidates, sorry?
The 75 that you find at the end that after you clean.
Oh, this is not working. Okay, so this is dominated by redshift, let's say around 1, more or less, most of the objects. But there is a table in the paper with all the redshifts. There are also lower redshift objects.
Okay, I will have a look then. And the other question is about the foremost targets that you have chosen. What are you doing with foremost?
So, okay, this is. So these are the key main objectives. So the first one is to understand the low black hole mass and low Eddington rate population and characterize them, specifically because in order to understand how supermassive black holes are formed and grow, we need to understand this population. For instance, the occupation fraction or the scaling relations between galaxy mass and black hole mass. We need to understand this low mass population to understand how black holes are formed. That's the first topic. Then we want to understand more about the physics of variability, because we will have access to light curves, and then we will have spectra. So we can derive physical properties, and then we can understand, okay, for instance, now we know more or less that the amplitude of the variability is mostly driven by the Eddington rate. But why? It's not clear yet. So that's the second part. And then the third one is to study these rare subsamples, where you have extremely variable AGNs, or changing look AGNs, or total disruption events. So that's, in summary, the three main.
But your target list comes from this work?
That's one of, okay, we have around 10 sub-surveys. And this is the main variability one. We have two variability. We use the same technique to classify data from Silla QUEST. I didn't have the time to show this, but that's another survey. And then the other part is with SED modeling. So that will be more complete in terms of type 2 AGNs. But today I show you most of the variability classification.
Okay, yeah, thanks, Paula, for a nice talk. You may have shown the answer I'm looking for, but I can't quite read the type there. So I think when you're past 25, it's a general question. Say talking about jet dominated, core dominated, and galaxy dominated, say AGNs. Can you roughly, from your samples, can you roughly say, are they more or less equally divided? Is there a class that dominates a class that's very few objects?
So
Thank you.
I think I have. Here, so in terms of populations, the core dominated are the more dominant in the ALeRCEs. You can see here. Also, in general, they are the more dominant. So these are.
I think this is biased by the variability pattern that you are looking for.
Yes.
Right? Because it's
and also because there are more sources, because the host dominated, you are only able to detect them in the local universe. Probably at high redshift with LSST, maybe we will go to these high redshift host dominated sources, but with CTF, as it's very shallow, we can only detect them at low redshift. And then blazars are a very small part of the sample. Oh, yes. Yes, this is from the optical. Yeah. Yeah. Yes, so actually, if you are interested in blazars, this model is very good. Yes. So we still have some confusion within these AGN classes because it's not it's a continuous distribution, of course. And in particular, you can have flat spectrum radio quasars that are also considered blazars, but they look more like quasars in the light curves. So that's why you have some confusion here. But if you're interested, the blazar are probably the population that we haven't explored yet. So you're welcome to take the candidates and use them. This is all publicly available.
A naive question for a final one is that if you took let's say consider M87, right? How far away can you detect it? Can you detect quote unquote, right? Can you classify one AGN like that up to which redshift?
I think with CTF in the very local universe.
Very local universe.
Yeah,
okay.
with LSST, I hope that it's not clear yet because it depends on when is this 5 sigma limit happening. But I hope with LSST we can go to higher redshifts.
Okay, thank you again, Paula.